In this video, we are going to discuss how to calculate chi-square tests through ArcCommander, and we're going to just use ArcCommander because it's pretty straightforward through this program, and there's really no need to do it in RStudio since it's pretty easy to do it in ArcCommander. So the first thing we're going to do actually doesn't require us to have a data set. We're going to type in the counts from data that have already been collected and kind of pre-analyzed, I guess you could say. So if you click on Statistics, Contingency Tables, and then enter and analyze a two-way table. So two-way refers to the number of variables. We have rows and columns, and we can indicate the number of categories that are within each row and column. So the default is a 2x2, and we're going to use the numbers that we used in class. So we had 75, 28, 33, and 81, and you just type those numbers in. Let's click on Statistics, and you can get different percentages, row percentages, column, and also percentages of total. You can only choose one of those, so let's do percentages of total. And then you can do different hypothesis tests, so you can do your basic chi-square test of independence. You can use the components of the chi-square statistic, and as I mentioned in class, that's a good way to figure out which of your cells are driving a higher value for your chi-square. You can print the expected frequencies, and you can also calculate the Fisher's exact test. So it's actually useful to check all of these boxes. Click OK. So we asked for several things. So first, it just recreates the table of counts, which is useful to have in your output. We asked for percentages of total, so that's what this is. So we have both cell percentages and row and column percentages of the total. Here's the basic Pearson chi-square, so the value 41.65 with 1 degree of freedom, a very small p-value. Here are our expected values. We asked for the chi-square components, so that's what it's giving us here. So this is the observed minus expected squared divided by the expected value for each cell. And then the Fisher's exact test gives us the p-value, the 95% confidence interval, and it's the 95% confidence interval around the odds ratio. So this would be the number, the 6.51 would be the number that you would report for the Fisher's exact test with a confidence interval and a very small p-value. So the Fisher's exact test is giving us the same outcome as the regular chi-square, which is that we would reject the null and decide that our expected values are not equal to our observed values. And then it's also possible to do this on actual data. You don't have to just type in the numbers. You can have raw data. And rather than loading a data set through R, we're going to do something a little bit different, because when you have your own data, it's not in R, and you'll need to know how to get your data into ArcCommander. So right now our data is in a .csv file, which is a comma-delimited file. It is something you can view in Excel, but it's a little bit different than an Excel file. So in order to get the data into ArcCommander, we need to click on Data, Import Data, and then the top option from Text File, Clipboard, or URL. Notice there are other options. If you had something in SPSS, SAS, Minitabs, Data, or Excel, you could use one of those options, but we're going to use the first one. And you can enter the name for your data set. The default is always data set, but you can certainly change it to whatever you want. We want to keep it checked, variable names in file, because our top row in our file is the variable names. The missing data indicator we're saying is NA, so you need to be able to look at your data and figure out if there's a different missing data indicator. And in fact, let's look at the data set quickly. So here's the data set. It's called Student Information. So here we have our variables in the first row. We want to read that in, and here we have a strange value, 999. And so in this data set, the missing value indicator is actually 999. So in ArcCommander, we need to indicate that by replacing the NA with 999. We're going to point to our local file system to read the data in. The field separator are commas, because we have a comma-delimited file. Decimal point character, we want to leave that as the period. Click OK. And then we find our data file. Again, it's called Student Information, so you can double-click And then it tells you here it's opened the data set with 46 rows and 21 columns. If you want to, you can click on View Data to look at it. Here we can see it replaced that 999 with NA, so that won't be included when you do statistics on that variable as an actual value. That's certainly important, otherwise it would have been a huge outlier. So once you've read your data in, let's say we want to begin with a goodness of fit test. And one of the variables is area. So let's look at the data set again. So area is the area that people are interested in going into. So it would be child, clinical, social, counseling, cognitive. There are actually quite a few areas. So one thing we might wonder is whether people are evenly distributed across these areas, or are people preferring a particular area over another? Is there an area that's more popular? So since we're just looking at one variable, we would need to do a goodness of fit test. So we can go to Statistics, Summaries, Frequency Distributions, and then we want to check chi-square, goodness of fit test. We don't actually care about the frequencies, we really want the chi-square. And the variable that we're interested in is area. Click OK, and then it gives you the factors. So in this case, there's 5 categories for this variable, and it's giving us equal levels across. So 1/5 in each of the areas is what our expected values are. We can change those if we wanted to make a different expected value prediction, but click OK. And so we get the probabilities here. They're in decimals instead of fractions. Obviously that's the same thing though. And then our chi-square test, 10.74 on 4 degrees of freedom with a p-value of 0.03. So here again we would reject the null hypothesis and say that our observed values are not equal to the expected values. In order to figure out what is driving that difference, we can look at the percentages or even just the raw counts across the areas, because our prediction was that they would be equal. So it looks like there's more people interested in child and counseling in the other areas, and only a few people who are interested in cognitive. So we can see what's driving that difference. The other kind of chi-square is the test of association. Remember, we use this test when we're interested in how 2 or more variables are related to each other. We want to know if there's independence across the variables. So one question we can ask is whether owning a pet is related to aspiring to get a PhD or a PsyD. Is there any association here? So let's go back to Statistics, Contingency Tables, and now we're doing a two-way table. And so we pick our row and our column. So in this case, we were interested in pet and PhD. We want to use all valid cases. Our options under Statistics, again, we can get percentages, and we can get the other types of hypothesis test information. So let's check all of those and click OK. So here is the top of that data. So first it's giving us the counts, that whether people have a dog or a cat, and then whether they're trying to obtain a PhD or not. So the highest value is people who are trying to obtain a PhD and own a dog. So then we have percentages just below that, and then our Pearson chi-square test. So our p-value is nowhere close to significant, so that means our observed values are pretty consistent with our expected values, and in fact here are those expected values. Chi-square components are all 0, and that's because our expected values are very close to our observed values. And then the Fisher's exact test, their 95% confidence interval, p-value is 1, and the odds ratio is about 1. And that is how you do chi-square in R Commander.